My name is Maiyu Diaz. I'm a math grad student from Texas Christian University, and today I'm going to be talking a little bit about a story of Stirling's formula. So everybody, I assume here, is familiar with the object that's called a factorial. It's an object that pops up in combinatorics, number theory, ring theory, and among very other disciplines. But the asymptotics for the factorial is something that I just want to focus on. And the study for this dates back to the 17th and 18th century, starting off with Avramoff, shooting off the studying asymptotics of this object, where he was able to show that n factorial behaves like more or less n the nth power with all these additional terms, when all this is multiplied by a constant k. It wasn't Demov that was the person that found the constant k. That was actually James Stirling, who was able to specify the constant k to be the square root of 2 pi. There are a variety of generalizations of the factorial. The complex analytic continuation that is provided by the gamma function. You also have the Q gamma function. But there is a generalization that was looked into by Bargava at the turn of the 20th century when he was attempting to generalize the following 4 properties of the factorial. The first one being that you have this binomial coefficients formula for the factorial. The second is that if you have a primitive polynomial of degree k, and then you're looking at the greatest common divisor of all the images of f evaluated at each input being the integer, then that number will always divide the degree of that factorial, of the degree of that polynomial's factorial. Then you have this Vandermonde determinant-like formula for any selection of integers that you pick out. That will always be multiple of these consecutive products of factorials from 0 to n. And then if I'm interested in counting the number of polynomials from normal polynomial functions from z to z mod nz, then it's given by this formula. And Bargava was interested in generalizing these 4 properties. So what he did is first he picked an arbitrary subset of the integers and fixed a prime p. And he wanted to construct a sequence called a p ordering of elements of S, and he did as follows. First, we pick an element from S, call it A0. The second element that we're going to choose is A1, and the way that this is chosen is that it minimizes the highest power p that divides this difference, A1 minus A0. Then I'm going to choose a third term that minimizes the highest power of p dividing these product of these pairwise differences, A2 minus A0 and A2 minus A1. And I want to continue with this process for each natural number such that then we minimize the highest power of p dividing these pairwise differences of products that we have here. So if WP of A denotes the highest power of p dividing A, and then we define this object here, V sub n of S of p, where we specify our n, specify our set, our subset of S of our integers, and specify our prime p, then we get a definition for the Bargava factorial, which is a Bargava factorial of a set or over a set S that is defined by the product over the primes of this number. And Bargava, for convenience's sake, decided to define 0 factorial for any subset S to be 1. So here are some examples of Bargava factorials for some set S. So if we have the integers or the naturals, we get back the factorial. If we have the even integers, we get a power of 2 hiding in there with the factorial. And then if I look at any multiples of the integers and shift it by some integer b, then it will just be a power of a. I get the Bargava factorial associated with that. Powers of q, I get these terms. And then I can just look at other interesting sets as well if I wanted to look at the Bargava factorial associated with that set, such as the squares, 1, 4, 9, 16, which is going to be 2n factorial divided by 2. And if I look at the set of primes, I get this interesting sequence that's associated with Bargava factorial, and same things with the set S prime. And S prime is a set that's determined from an associated sequence that's from Tesch's algorithm. So earlier I mentioned that we were interested in the study of the asymptotics approximations of the factorial. Bargava, in his paper, Factorial Function as Generalizations, he wanted to look at an analogous question to that associated with, instead of the factorial, it'd be with these Bargava factorials. That is, what are the analogs of Stirling's formula for generalized factorials? I'll admit, this is a really hard question. So I was pretty optimistic at trying to get the full Stirling's formula, and my heart was broken. So instead, if we try to look at a weaker form, that is, if we have a representation of log of n factorial that's given by this up to on, can I get something of the form log of the Bargava factorial over some arbitrary set S
will look something like this: an plus on of n to the c, n to some c power. Well, earlier that when I was talking about for some sets, they noticed that they all either depended on the factorial, which we know we can get the Stirling's formula for that, or the Q gamma function, which is known to have a Stirling's formula, which was discovered in the early mid 20th century. But for sets of prime p, or for s prime as an example, those were not known. But in this work that I was has been accepted for publication this year, I was able to derive the weak Stirling's formula for these two sets. So for over the primes, we get this constant that's hiding out in front of the n, where we have the sum over p prime of log p over p minus 1 squared, and is approximately 1.2269, etc. And for the set S prime, we get this little bit more of an atrocity, but still we were able to get a representation for S prime. So where do we go from here? And what do I mean by this question? Earlier, I mentioned that can we get a weak Stirling's approximation without up to on or up to on to some power? But what if I wanted to specify that on? We're going to have to look into some deeper number theoretic objects here. So if I just look at the factorial, for example, first, I know what my Riemann zeta function is, which for complex sets with your part of s being greater than 1 is defined by this infinite sum. And these are what are the four nice properties that are associated with the Riemann zeta function. It's zero free for the half plane greater than 1. It's a meromorphic continuation beyond the half plane. It has some poles. We have a simple pole s is equal to 1, and we know that it has some zeros. We have the trivial zeros and the non-trivial zeros, which are conjectured to lie on the critical line. And as it turns out, we can actually get a relationship between the factorial and the Riemann zeta function via this contour integral representation. In particular, we're looking at the derivative of the Riemann zeta function. So here, using the fact that the derivative has a double pole s is equal to 1, we can actually recover the weak Stirling's approximation for log m factorial. But if I wanted to specify my on term, that's where we start running into convergence issues with the integral. But this, even though originally posed a problem, it actually can be amended. So there is another type, a function that looks like the Riemann zeta function, and it's called the Dedicant zeta function, which is defined by these characteristics. We have an algebraic number field that's defined over the half plane, defined over the sum, where I ranges through the non-zero ideals of the rings of integers OK of k, and that denotes the absolute norm of our non-zero ideal. The Dedicant zeta function shares just about the same properties as the Riemann zeta function. It's zero free over the half plane, has a meromorphic continuation beyond the half plane, has poles, a simple pole s is equal to 1, and has some zeros. But instead of the Riemann hypothesis, we have something that's called the extended Riemann hypothesis, but the concept is the same, that they lie more or less on the critical line. In 2014, Matthew Lemrow observed the factorial of a number field, which is given by this formula, which mimics the Legendre formula for the factorial. And he derived a contour integral representation for this factorial that depends on the Dedicant zeta function, where we have these additional terms just popping up over here. And we have inside the contour integral a logarithmic derivative of the Dedicant zeta hiding in there. And then we have these bk sub n terms, which are the Dirichlet series coefficient of the product of the negative of the logarithmic derivative of our Dedicant zeta function and our Riemann zeta function. So the original factorial in the contour integral representation had problems with the convergence issues, but Matthew was able to overcome these convergence issues, and he was actually able to get a Stirling's formula, where it's given by this information here. So we have R1 and R2 hiding up on the power of the square root here, which is the number of real and complex beddings of K on Q. We have the Euler-Kronecker constant, which is given by this limit. And we have the CK of n term, which is given by the degree of the extension K over Q. We have the Euler-Mascheroni constant hiding there. We have the discriminant of K, and then we have this SK of n term, which looks at over the sum of these terms over here that depend on the zeros that the Dedicant zeta function takes in between 0 and 1. So given this information, I asked myself, can we do something similar with the Bargava factorial? So if I define the S zeta function for S defined as such for real part of S greater than sigma of S, where sigma of S is defined by this limit, which denotes or is defined as the order of S, and I have this von Mandt-Gold looking function, which is defined by this term, I ask myself, is this zero free? Does it have a meromorphic continuation beyond the half plane, for which it's greater than for which real part of S is greater than sigma sub S by some functional equation? Does it have any poles? And does it have any zeros? So if I just assume these things with some quote unquote finagling, we can actually get a contour integral representation for our factorial, where we have this information that's mimicked from the concept behind the Dedicant zeta function. The problem is here that unlike the Dedicant zeta function, whereas those 4 pieces of information are known, this is not known. So there's not much that we can do here beyond this representation that we have here. So that said, we can actually have an idea of what to expect now, because the representation for the Stirling's formula for a Brigada factorial looks like it's going to be coming from information on these what they're called L functions. So the conjecture here is that if we have these 4 pieces of information, we can actually get the weak Stirling's formula for our Bargava factorial, which is given by the residue evaluated at sigma sub S on this function.
You're done?
Yes.
Oh, okay. Let's discuss.